Hi, so today we're just going to be talking through some McCabe Thiele diagrams because I know they can just be a little bit difficult to grasp if you've just gone across it in class really quickly. Just wondering what all the components are, what it's doing, why it's there. So first of all, we're starting off with a vapor-liquid equilibrium. So that's just this equilibrium line and this x equals y line. So I've got it for monochlorobenzene and phenol in front of me. So the monochlorobenzene is going to be the more volatile component. You can always check that out online just by googling boiling points, and that makes sense chemically. That's just the more volatile component here. So this is just going to be X. This is all of MCB. So that's also referred to as component A, the more volatile component. So the first thing you just need is to generate this VLE. So you generate the VLE from a data table, something like this. We've got antimony constants. So this is at 716 millimeters of mercury, just a little bit above 1 atm, just above atmospheric. Really, I've generated it from antimony constants here. You can generate it from relative volatilities, anything like that. But basically, as long as you've got your equilibrium curve, you can plot it onto your graph, that's all good. The next thing you've got is you've just got this tie line of x equals y all the way up. It's just useful because lots of your points fall onto this line, so you can see it visually, and it helps just to create this bow shape which you're going to be using. So the only things that you really need to know to create your McCabe Thiele, which is just going to model your separation really of a binary mixture, is your reflux ratio, your feed fraction of A, and from that you can obviously work out your feed fraction of B, because it's just going to be 1 minus your feed fraction of A, so just got 0.7 here for the phenol. That's also it. You need to know your top separation and your bottom separation. So all this number is saying is that my liquid mole fraction of my A component coming out the top of my column is going to be 0.95, so it's 95%. So out of my top feed is going to be 95% monochlorobenzene, and it's going to be 5% phenol. And then again, vice versa. For the bottom, it's going to be 0.1, so 10% monochlorobenzene and 90% phenol at the bottom. So that's all these numbers are telling me. You'll be told exactly what you might do calcs to work out what they are, or you'll be told what to set them to. But as long as you've got this set of data that I've highlighted in yellow here, that's all you really need, along with your equilibrium line, to generate this McCabe Thiele separation diagram. So the first thing that you need to do is generate this Q line. So all this Q line actually is, because it takes a little bit of time, well, it took me some time to grasp it, so it's the state which your feed is in. So is it a vapor, is it a liquid, is it saturated, is it not? So a Q line with an infinite gradient, so Q equals 1, is just going to be a feed at its saturated liquid temperature for that pressure of your system. So anything that arrives as saturated liquid is just going to have this vertical line. Often you'll find, especially in first years, second year maybe, you'll see a lot of stuff entering in your questions at its saturated liquid point. All that means is that the lecturers are expecting you to know that this line is just going to be vertical. If they don't say that, then you're going to need some thermochemical data sheets to know where your Q line is meant to be. So there are ways of working that out. If you've covered that in class, then you might be expected to, but often what I found in exams is they're going to expect you to rely on this knowledge that at a saturated liquid point, it's just vertical. So all that's done is just construct this line here. Moving on to your toll section, so here's my top operating limit. the first point that you always plot on here is xt, xt, so that's just your top separation point. It's always going to lie on this x equals y line. It's just this green dot here. And from that point, then you can just help generate this tall line, so top operator limit line. Then the next point that you need to plot, and this is really the only maths that you're going to need for generating these, is your intercept with your y line. So I've got, you also know that x equals 0 at the y-intercept, and then you just need to use this quick formula here. So as you can see, you've got my xt, my top separation, over my reflux ratio plus 1. So that's going to give us a value just above 0.3. So you can see it would be pulling in around about here, be crossing the axis, which makes sense with the line. And then a good point just to think about with this is that if your reflux ratio is increasing, what's going to happen? So this value is going to be higher because it's on the denominator. It's going to make it's on the bottom of the fraction, so it's just going to make everything, the value, smaller. So you divide by it. So larger division is just going to make this value lower. If this value is 0.2 or if it's 0.1, I think you're being drawn down further towards the x equals y line. So if you're down here, then this means it's just going to have more space for your stages to step down, and you're going to need less stages, so the separation is effectively easier. So that's just something to think about. We've got a higher reflux ratio, you can have easier separation. That's graphically why. So moving on from that, just got your bottom separation. Ball. So I've got my ball line graph down here. Trend line. All it is you're starting from your bottom separation point, 0.1, 0.1. It's always going to lie on this axis as well, this x equals y line. And then you just need to step up until it hits your tall line. So your tall line and ball line always intersect at the Q line. So for this it's just simple because we know it's always at 0.3. So we can go and just fill in these to be equal to the value of these right here. So just make them all line up nice and simply. Yes, so as long as those line up, then you've got this bow and you've got all the lines that you really need for your separation. All you need to do then is add in the plates. So if we just go across the plates, then I've got macros here working it out. But effectively all you're doing is you're just going across horizontally until you reach this equilibrium line, and then down until you hit the tall or ball respectively. So either side of the Q line depending on where you are. And that's all there is to it. So you can just count these separation stages. So you need to keep doing them until you get a down line, vertical line, which is going to be equal to this x equals y. So as you can see, I'm missing one on this, so I thought that'd be a good idea to add it in. So we just get to select data, and we can just add a plate. So I'll just call that plate 5. And I've got them here, so for the x, and for the y, and then add a down 5. I've got the x and y. So there you go. We can see we've hit this x equals y, so the separation is complete. We've got 1, 2, 3, 4, 5. So you can always count the horizontals. You've got 5 plates required for this separation. And you can see that your feed is going to come in on your 1, 2, on your third, on the third plate. So it's always going to be on your third plate there. So that's a nice way to work out what your feed point is for your column. And knowing that this point is always just going to be equal to x equals y, so you can just write out like some if rules if you wanted. to know that if your value should be down here, nothing can ever drop below this x equal y line for your column. So yeah, I think that's everything really that you need to go through, everything you need to know. It's just that one real simple formula here that you need to know for when you're looking at these McCabe Thiele diagrams. And then you've got your vapor fraction up to the y-axis, your liquid across the bottom, and that's everything really. You can do these just by drawing them by hand, so that's just a hand-drawn version. It'll be really similar, it'll be really close. It's always nice to have some automated computerized ways of doing them, so you can do them on MATLAB as well. It's quite a nice way to do them, because then you know it's just fully accurate. You don't have to worry about them. Thanks a lot, hope that was useful. That's everything from me, bye.